All right, starting section 11.3, the integral test and estimates of sums, which we're not going to get into the estimate part of this. I'm going to shorten this section a little bit, give you a little less to worry about. But what we're dealing with over the next several sections, 11.3 through 11.6, are going to be a bunch of different test processes that we can use to determine whether a series is convergent or divergent. And we talked in the previous section, convergence or divergence of a series. We talked about geometric series, which we have a way to determine whether those are convergent or not. It's depending upon the R value. If R is between -1 and 1, we had a convergent series. Otherwise, it was divergent. We also, in the case of the geometric, could calculate the sum. We had a formula for that A over 1 minus R, if we had a convergent geometric series. Other than that, though, I kept telling y'all, it's not always an easy thing to determine the sum of a series. It's a lot easier to determine whether there is a sum, but finding the sum itself is a lot more problematic. And so we can do that for geometric series, but that's just one specific type of series, and we can actually calculate the sum. So we're going to focus on the remaining part of this, the remaining sections, or the next several sections, is at least being able to determine whether the series is convergent or not. Okay, now the estimates of sum part of this, I'll include the notes here. You can look at that if you're interested, but I'm not going to test you on that. I'm not going to ask you about that. But the idea there, of course, is, if I can't calculate the sum exactly, can you at least give me an idea, right? Can we at least come up with a way to estimate the sum of the series to within a certain degree of accuracy? Now also in that previous section, we did mention another test, the test for divergence, which was the one that said that if the series is convergent, that the limit as n approaches infinity of the terms of that series, the limit as n approaches infinity of a sub n, has to equal 0 if the series is to be convergent. Right? So the test for divergence said that if that limit is not 0, I can at least tell you the series is divergent. If it is 0, I can't say that it necessarily converges. We did have that harmonic series as one example that showed us that it was a divergent series even though the limit of a sub n was 0. So what happens if the limit as n approaches infinity of the terms a sub n is 0? Right? So I can't tell you if it's convergent or divergent. I have to make that determination. That's where all these other tests are going to come into play. Right? So this integral test is going to be one of those. Now the integral test ends up being, well, I guess this would be true for all of the series. We keep saying it depends on the type of series. You have to recognize the makeup of the series, what it looks like, which test is going to work for a specific type of series. So it's like what we did with the integration, recognizing the type of integral that you're working with. So what method did I use for integration? The same thing is going to be true for convergence and divergence of series. And so you have to recognize the type of series and which test you can apply to that specific type of series. All right, so this integral test, though, is pretty specific in terms of what type of series or the series that you can use it with, right? Or at least it has to meet certain conditions. So that we'll talk about that as we go through. Right. So getting into the notes, right? So we say it's not always easy to find the sum of the series. We know, though, that the sum of the series would be the limit of the sequence of partial sums. But again, there's the problem with some of this, finding the value of that limit. So there are these other tests that allow us to at least determine whether the series is convergent or divergent without necessarily finding the sum. Right? Starting with the sum, as n goes from 1 to infinity, of 1 over n squared. Look at the terms of that series, right? So plugging in values from 1 to infinity, so I've got 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, etc., etc. And we have constructed here a table showing some of our partial sums. Right? For n equals 5, s of 5, our fifth partial sum, s of 10, s of 50, etc., up to s of 5,000. Right, now, we said in the big scheme of things, even adding the first 5,000 terms is not very much. I mean, you're talking about, again, an infinite number of terms. 5,000 compared to an infinite number of terms is meaningless. But you even start to see at that point, even just adding the first 5,000 terms, it appears that that sum is approaching approximately 1.65. Right? Looking at this graphically, And this is the part that we're interested in. Now, I'm going to go back to, let me remind you of something we've talked about previously. Let me do this first and then we'll get into this. Back in section 7.8, we talked about integrals, those indefinite integrals, say integral from 1 to infinity of 1 over x to the r. And we showed that if we evaluated that integral, and you had to go through that whole limit as t approaches infinity. Maybe to go back and review section 7.8. Right? Those are those indefinite integrals, the limit integrating to infinity, or where we had vertical asymptotes. But if we looked at the integral from 1 to infinity of 1 over x to the r, we showed that this was convergent if r was greater than 1. And we showed that this was divergent for r values less than or equal to 1. Now, I have this stated later on in this section, but I just want to mention that at this point because I think it'll help in our discussion of these first couple of examples that we're going to look at. All right, so this is something that we did show. We proved this back in section 7.8. So an integral of that form, 1 over x to the r, as integrating from 1 to infinity. We showed was convergent if r is greater than 1. We showed it was divergent if r is less than or equal to 1. Okay, so keep that in mind as we go forward. So then I'm looking at this graphical representation now. Instead of using the series 1 over n squared, I'm graphing the function y equals 1 over x squared. All right. And I'm just looking at that part of the graph that's to the left of the y-axis. And because that's, of course, where then our x values are positive. Comparing that to the series 1 over n squared. Okay. Now I'm forming the rectangles, finding the area under the curve, and we did those approximation techniques where we would draw the rectangles and find the areas of the rectangles. Remember our sum of the, I brought in our whole sum notation, and we had the midpoint rule and all of that. So this is using the rectangles to approximate the area under the curve, and I want to see the comparison here. Look at each of the rectangles that I have formed. Now in this case, and this will be a little vague at first, but I'll explain, and it'll maybe make more sense once we get done with this. But look at each of the rectangles that I have drawn. The first rectangle, right? The width of that is from 0 to 1. The height of that rectangle is the function, right? So 1 over 1 squared. The second rectangle has, again, a width of 1. The height is the function, or determined by the function, right, where x equals 2, so 1 over 2 squared. The third rectangle, width of 1, the height is 1 over 3 squared. But if you look at the areas of each of those rectangles, look at that first rectangle. Width is 1, height is 1. Second rectangle, width is 1, height is 1 over 2 squared, or 1/4, so the area would be 1 times 1/4, or 1/4. The third rectangle has a width of 1, height of 1 over 3 squared, or 1/9. The area would be 1 times 1/9, or 1/9. But the bigger observation is, look at the areas of each of those rectangles. They're exactly the same as the terms of our series. Right? That first rectangle has an area of 1 over 1 squared, the second 1 over 2 squared, 1 over 3 squared, etc. Because in each case, the height is multiplied by the width of 1. So I'm looking at each of those rectangles, the area of each rectangle, corresponding to a term in our series, as n goes from 1 to infinity. Now, a couple of things I want to notice here. First of all, if I was to integrate this function, 1 over x squared, from 0 to infinity, we couldn't integrate from 0 to infinity, because remember that there's a vertical asymptote here on the y-axis. There's that gap between our function and the y-axis. So that, again, was one of those improper integrals with a vertical asymptote, where we would have to look at the limit as t approaches 0 from the right and go through all of that. I'm just going to start this at x equals 1. So in other words, let's just ignore this first piece of the rectangle. And let's look at the integral from 1 to infinity of 1 over x squared. And we'll take this piece, this first rectangle, to have an area of 1 square unit, and we'll just add that to that integral from 1 to infinity. Right? Because remember, the integral represents the area under the curve. Right? So I'm going to take the integral from 1 to infinity, look at the area under that curve, and then we're just going to add this extra rectangle to that. Right? So add 1 to it. Now, that's the first thing to remind you of, right? So we can't integrate from 0, so I'm just going to start this at 1. Also recognize that the area of each of those rectangles, right, since the rectangles are under the curve, the area of each rectangle corresponds to each term of our series. But if I add those terms together, as n approaches infinity, adding the areas of each of those rectangles is going to give me a value that's smaller than the area under the curve. Right? Because each of those rectangles is an under approximation of the area under the curve. And so if we look at the integral from 1 to infinity of that curve 1 over x squared, area under the curve, whatever that area is, it's going to be larger than the sum of the areas of each of those rectangles, right? And that again is obvious because the rectangles are below the curve. So keep that in mind as we go over to our next slide. So adding the area of the rectangles, the total area of the rectangles is less than the area under the curve, y equals 1 over x squared. We can't integrate from x equals 0, so we just cut out that first rectangle. We let x be greater than or equal to 1. So the area under that entire curve would be equal to the integral from 1 to infinity, plus there's that extra 1 that we had for the area of that first rectangle. Now, this is an integral that we did calculate back in section 7.8. And this is how we came up eventually with the observation about that integral of 1 over x to the p, or 1 over x to the r, as from 1 to infinity. And we showed that that integral actually converges, and the area under that curve is 1. So what does that give me in this case? Well, since the integral from 1 to infinity of 1 over x squared equals 1, and then we're adding that extra 1 square unit, right, from that first rectangle, then I know the integral from 0 to infinity of 1 over x squared, the area under the curve that we originally had, has to be at least 2. Now there's that little extra piece on the other side as well from that, from this, okay? But I know this area equals 1, and then we're adding this piece, this rectangle of 1. So that's where this 2 is coming from. Now, since the area of the rectangles is smaller than the area under that curve, then we know the area of the rectangles, the sum of those areas, has to be less than 2. Right? Because again, I've got the first rectangle, which is 1, plus the area under our curve, which we said is 1, but our rectangles have less area than the area under the curve. So I'm making the observation then that our sum as n goes from 1 to infinity of 1 over n squared has to be less than 2, because that's the area under that curve of 1 plus that extra 1 rectangle. Okay. So since our partial sums, now they're increasing, and they're bounded. We talked about that monotonic sequence there. I've got these partial sums that were getting larger, and we showed they were approaching 1.65, but they were getting larger. They were bounded above. We know that the area under that curve is 1 plus the area of that extra rectangle. So we know that the total area can't exceed 2. The partial sums have to converge by that monotonic sequence theorem. And that was the theorem that said if you had an increasing sequence that had an upper bound, or a decreasing sequence that had a lower bound. In this case, it's an upper bound, just depends on which direction we're headed. But since that sequence of partial sums is getting larger, and I know it can't exceed 2, then I know that that series has to converge, because the integral is convergent. Right? Now, somebody actually found this sum. They found the sum to be pi squared over 6. Now, and that takes a lot more work than what we're doing here, but it can. Some of these can be found. That'll take some higher level math to do some of that stuff. But yeah, so at least we know this does converge. So at least we knew there is a sum. Okay. Look at the next example. I've got the sum as n goes from 1 to infinity of 1 over square root of n. So it'd be 1 over square root of 1, 1 over square root of 2, 1 over square root of 3, etc. Right. Again, I've got the partial sums, some of them listed from 5, 10, 50, 100, etc. up to, again, 5,000. But notice in this case, if you look at those partial sums, right, they're getting larger, of course, but they're not approaching a number, right? They're getting larger without bound. Looks like they're getting infinitely large or approaching infinity. So again, I'm going to compare this to the graph of the function y equals 1 over square root of x. Now notice in this case, and this will be a little bit vague at first, but I'll clarify as far as why we're doing this. Remember with that first example, we drew the rectangles here. Scratch that. Right. So I did the first rectangle there, and then the second rectangle there, and the third rectangle there, right? And so then when we compared our area under the curve to the area of the rectangles, right, the area of the rectangles was smaller than the area under the curve. Right? In this case, notice I am putting the rectangles above the curve. But again, each of those rectangles has a width of 1. The height is determined, in this case, by the left endpoint, which x equals 1, n equals 1. The area of that first rectangle is 1 times 1, or 1. The second rectangle, again, has a width of 1. The height is determined by that function, 1 over square root of x, or 1 over square root of 2 in this case. The third rectangle, width of 1, height 1 over square root of 3. Okay? But again, I've got the area of the rectangles corresponding to the terms of our series. But this time, each of those rectangles is an over approximation, right, of the area under the curve. And so whatever the area under that curve is, from 1 to infinity, I know that that area has to be smaller than the sum of the terms of our series. Right? And this is actually, here's our first term, here's our second term, here's our third term. Right? A sub 1, A sub 2, A sub 3. Okay. But the comparison here is different. Right? The area under the curve is less than the area of the rectangles, or the area of the rectangles is greater than the area under the curve. But this time we can actually look at that integral from 1 to infinity. I don't even need to consult what happens between 0 and 1. So the total area of the rectangle is greater than the area under that curve, 1 over square root of x, for x greater than or equal to 1. But this goes back to our series, or our integral, right, that I reminded you of in that previous section, that 1 over x to the r, because in this case, r is 1/2. And since 1/2 is less than 1, we showed that that would be a divergent integral, that the area under that curve was infinite as you integrate from 1 to infinity. And so here's the important observation then to put comparison. Since the area of our rectangles is larger than the area under the curve, as n goes from 1 to infinity, the sum of 1 over the square root of n would have to be then greater than the area under the curve, 1 over square root of x, for x greater than or equal to 1. And that's our integral from 1 to infinity. Now, again, that's a little tricky because, in the first case, I put the rectangles below, or showed that they were an under approximation. In this case, they were an over approximation. Okay? There's a reason for that. But at least I can make this comparison that since the integral from 1 to infinity of 1 over square root of x is divergent, the sum as n goes from 1 to infinity of 1 over square root of n has to also be divergent, because the area of the rectangles, the sum of the terms of our series, is greater than the area under that curve. Okay? Now here's why I made the comparison the way that I did. What if I had an integral, I'm just going to say 1 over x to the r, something of this form. They're all going to have the same basic shape from 0 to infinity. They're all going to look like that. And I'm just going to say integral from 1 to infinity. We'll start there. In the first case, I drew the rectangles starting with the right endpoint as our end value. Right? So n equals 1, n equals 2, n equals 3, etc. But in each case, the area of the rectangles was smaller than the area under the curve. In the case where this was a convergent integral, right, where r is greater than or equal to 1, greater than 1, excuse me, then the fact that the area of our rectangles is smaller than that convergent integral shows me that I have a convergent series. What if this was a divergent integral? What if the area under that curve was infinite? The fact that our area of the rectangles is smaller than the area under that curve doesn't help, because if the area under the curve is infinite and the sum of our area, the sum of our rectangles, the sum of our terms is smaller than that, that doesn't help in determining convergence or not. All I can tell you is, well, it's not infinite, or it's less than infinite. But what does that mean? Right? Take it in the opposite direction. When we draw the rectangles above the curve, so using the left end point as our boundary point, right? So like we did with our second example. And so then I used 2, and I used 3, okay? In this case, the area of the rectangles was larger than the area under the curve as x goes from 1 to infinity. And that's fine, because the area under 1 over x to the 1/2, right, 1 over our square root of x, is infinite. And since the area of our rectangles is larger than that value, than this area, then I know that my series would diverge because the area represented by those rectangles is larger than the area under the curve. What if instead, though, I drew the rectangles this way, but this curve represented a convergent integral? So say for 1 over x squared, if I'd drawn the rectangles this way, we know the area under this curve was convergent. We know the integral was convergent. The area was 1. But the fact that our rectangles are an over approximation of that, again, is not going to tell me anything. I can't say that that is a convergent series because the area of the rectangles is larger than the area under the curve. Now, yeah, that still seems confusing. Let me say it this way. I think this is the best way to look at it. With this type of comparison, and this is what the integral test is ultimately going to tell us. If I can compare my series to an integral that we know converges, and I know that the terms, the partial sums of my series are always going to be smaller than that integral, then I can tell you that my series has to converge, because our series, the sum of our series, is smaller than a convergent integral. And then vice versa. If I can show that the terms of my series, that the sum of my series is larger than that of a divergent integral, then I'll be able to make the observation that our series has to diverge. So in other words, I have to either have a series that is smaller than a convergent integral to say it's convergent, or it has to be larger than a divergent integral to say that it's divergent. If it's smaller than a divergent integral, that doesn't help. If it's larger than a convergent integral, that doesn't help. Right? So keep that in mind going forward. I mean, that's gonna come into play with some of these other tests that we're gonna talk about. Mainly what we call comparison tests. Okay. You've got to be careful with what you're comparing it to because you need the proper comparison to make the proper observation. All right, so here's the integral test, and here's the bottom line with this. So, as usual with a lot of this stuff, that's all the layout of it. Here's the integral test. All I really need you to know is how to apply this thing and to recognize when to use it. Now, the integral test has some limitations, has some specifics. Suppose that our function f, or we have a function f, that is continuous, positive, and decreasing. So there are 3 requirements for our function in order to use the integral test. We have to have a continuous, positive, decreasing function on the interval from 1 to infinity. Now, ultimately, we've said this before, it doesn't matter where you start because you're going off to infinity. The left bound is irrelevant. It's all about what happens as this thing approaches infinity. But the general definition, integral from 1 to infinity, because for our series, we're always starting at n equals 1. And we'll let a sub n, we'll let the terms of our series be equivalent to the function values at n. Right? So a sub n is f of n. Take our function f of x, evaluate it at the different n values corresponding to the terms of our series. Then the series, sum of a sub n, is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. Okay? And so what that's telling us, and you can take it both ways, if the integral from 1 to infinity of f of x is convergent, then the sum as n goes from 1 to infinity of a sub n is a convergent series. If the integral from 1 to infinity of f of x is divergent, then the sum as n goes from 1 to infinity of a sub n is also divergent. Right? So, you don't have to worry about showing if it's larger or smaller or all of that. We've gotten to this point with the integral test where as long as you meet these requirements, and that's where this comes into play, and I can't emphasize that enough. In order to use the integral test, this first has to be true. It only applies or can be used for functions that are continuous, positive, and decreasing. Okay? Otherwise, the integral test is not reliable. I can't make the conclusions that we've just got through making. All right, so back to section 7.8 again. You may need to review some of that, and this is what I mentioned earlier, that integral from 1 to infinity of 1 over x to the r. We're going to use p now, because eventually we're going to call these p series. So 1 over x to the r, 1 over x to the p. We know that this is a convergent integral if p is greater than 1, and divergent if p is less than or equal to 1. And like I said earlier, you don't have to start necessarily at x equals 1. It's all about the fact that it's an integral or a series that is approaching infinity. Right? So integral from a to infinity. Just be careful of the domain, right? We always had domain issues, just like the original one. The first one we did, we couldn't integrate from 0 to infinity because we're undefined at 0. Okay? Domain issues always in play. The next one, again, this would be a case where 1 over n square roots of n, or 1 over n to the 3/2. So that would fit that format of p or r greater than 1, which should lead us then to a convergent series. Now, why is the series convergent? Now, you want to be careful here with your statement. Why is this series convergent? Because the sum of that series is less than a convergent integral. Okay. Summary. Call these p series. The sum as n goes from 1 to infinity of n 1 over n to the p. This is a convergent series if p is greater than 1, divergent if p is less than or equal to 1. Right, so this is going to be a special type of series. Call this a p series. Notice that now when we talked about that harmonic series in the last section, 1 over n, that's a p series. Just happens to be a p series with p equal 1. Okay, so the harmonic series is a p series. The p series is the more general form. But the harmonic series is just a type of p series. Okay? So we call these p series convergent if p is greater than 1, divergent if p is less than or equal to 1. Right? So you don't have to do any fancy footwork here. Right? I have a series that fits that format. We can make that direct observation. You don't have to go through any fancy process. Otherwise, though, this integral test can be used for other functions or other series where their corresponding functions meet those three requirements: continuous, positive, and decreasing. Now, also keep in mind that the sum of the series is not equal to the value of the integral, right? So, I can evaluate the integral, and in the case of a convergent integral, I can give you the value of the integral, or at least approximate that. That is not the sum of your series, because we are still saying that the sum of the series is smaller than the area under that curve, right? That was all the little rectangles, right? The rectangles are the terms of the series. For the convergent series, they're smaller than the area under the curve. So we're using the integral simply to determine whether the series is convergent or divergent. But in the case of a convergent integral, the sum of the series is not equal to the value of that integral. Okay? Now, again, when you're making your statement about these, you're going to evaluate the integral and say, okay, let's compare this to the integral of f of x. Show whether that integral is convergent or divergent. And then if the integral converges, then I can say my sum is convergent. If the integral diverges, I can say the sum is divergent. Right? But that's the reasoning. So be clear, be careful. But again, it does have to fit those requirements. So over the next few sections, we're going to talk about more tests, and that'll become a lot more of the process in determining, all right, which tests can I use for different types of series based upon the makeup of the series. That's the main part of this section. The last couple of pages that I have, the notes, have to do with that approximation, so estimating the sum of a series. I'm not going to get into that. I'll spare you some of this, but you have nothing better to do Friday night, you're bored, or really any time now since we're all locked inside. Feel free to read through that. But you can actually, there are ways to approximate, or at least reasonably so, come up with a way to approximate the sum of a series within a certain degree of accuracy. And you can actually set the degree of accuracy that you want. So it's said, okay, can I give an approximation to the series, to the sum of the series, within set parameters. Right? So it's kind of like we talked about approximating with area under curves before, whether or not I can actually calculate the area under the curve exactly, but at least I can approximate it to within a degree of accuracy. Right? All right, that's the integral test. So, it's one that we don't really, I think, compared to some of the other tests we're going to talk about, one that we probably don't use that much, right? But, yeah, because it is very limited in terms of the types of functions that you can use it with. All right, that'll be it for that section. See you in section 4.